We are going to conclude this course with a quick look at regression analysis. Actually, it's not going to be very quick in the sense that this class is going to be probably one of the longer ones, but hopefully it's going to be worth it because regression analysis is a very common procedure, and as usual, there are a number of things that you need to know about it in order to be able to assess it properly. Now, first of all, a little bit of a reminder. We have seen in the last class that correlation coefficient and scatter plot together may reveal the presence of a linear relation, right, between two variables. So we may have a scatter plot that looks like this. Usually that corresponds to a correlation coefficient close to 0. We don't see any pattern, so we can come to the conclusion that the two variables we're looking at are not related to each other. Or we may see something like this, which shows a very clear upward pattern, and it is linear. Therefore, the correlation coefficient is going to be very close to 1. Not exactly 1 because the lines, the dots are not exactly along a line, but pretty close to 1. And of course, you can have situations like this as well, where we do have a pattern, but the pattern is not linear, and we don't have any idea what the correlation coefficient might be. Or if we look just at the correlation coefficient, it may not really tell us anything at all about the presence of this curved pattern. So we looked at the question of if there is a relation, right? But what we're going to be looking at right now is how do we identify the relation itself if we know that it exists, right? And once we know what the relationship is, how can we put it down as a mathematical relation so that we can hopefully do something with it? If there is a linear relationship, so we assume that such a relationship exists between two numerical variables of interest, so we assume also that our variables are numerical. Again, occasionally we may also use ordinal variables as long as they're pretty close to being numerical. But under these conditions, well, which formula represents it? So how can we relate the two variables x and y through some kind of mathematical formula? And the other issue related to it is that, of course, if we're using statistics, it means that there is some kind of random variability. Well, how does that variability affect this relationship? So these are the two key aspects. The most important one is what formula represents it, and also within that formula, how does randomness play its role? If you think about it, answering this question is pretty much impossible. Why is that? Well, because as it is, the question is way too vague. We're looking for a function. Well, there are infinitely many functions of different types, of different forms, of different conditions. If you have done any little bit of work in algebra or even more in calculus, you know that the variety of possible functions is literally limitless, but I mean, it's more than limitless. I mean, there is just way too many. Okay, so what we're going to be doing is we're going to have to limit our options. So for instance, let's say that we have collected a bunch of data and they give us a scatter plot that looks like this. What kind of pattern are we looking for? We could be looking for a fairly simple, straightforward up pattern. We can see that the relationship between these two variables seems to exist and it's upward. We can simply start simple and say, well, let's assume that this is a linear pattern, and let's find out what the linear pattern is. Or we could say, well, wait a minute, there is a little bit of curvature in those data, so maybe what I should be looking for is some kind of a curved pattern that encompasses or describes those data a little bit better. Or I may be real nuts and say, well, what I want is a pattern that really catches each and every one of my data. Okay? So which of these options are we going to be looking at? Well, we definitely need to make some assumptions in order to make this work. Otherwise, once again, there are way too many options, too many possibilities. Now, the common assumptions that are normally made are these ones, and I'm going to explain to you both what they are and why people make these assumptions. The first one is that we're going to be looking for a linear relation. Okay, so we are going to be looking for some kind of formula that looks like y equals mx plus b, and I'll say a little bit more about this equation, refresh a little bit your memory on it in a minute. So we are in fact going to assume that the relationship is straight. Okay. Also, we're going to be assuming that all the random variability is in the response variable, in the y variable. I'm going to say something more about whether it's okay to call this the response variable in general, but again, we're assuming that it is in the y variable. That means that our model will be basically y equals mx plus b, but plus some additional variability. So we're going to assume that this is what's actually happening. Given any value of x, the value of y is given by that linear formula mx plus b plus some random variability. So let me refresh your memory on this formula which describes the equation of a line. When I write y equals mx plus b, what I mean by x is the input variable. Now, input into the equation, not necessarily input as in cause in the relationship that comes from the statistical analysis. Remember, in statistics, we can only talk about correlations between variables. We can only say that they're related, but using statistics only, we cannot really claim any cause-effect relationship. So we're still going to be talking about the input or the generating variable, even though it's not necessarily related to a cause-effect relationship. So therefore, the y variable is what I'm going to be calling the output, even though again it's not necessarily the effect of my relationship. So theoretically, our data should be falling on this line y equals mx plus b. Of course, because of the random variability, the observations will not be exactly on the line, but there will be somewhere around the line. Okay, what about the m and the b? What do they represent? Well, the m is what we call the slope, and if you may remember, given any line, what I can do is I can look at a little chunk of it and figure out what its run and rise are, and then the slope is going to be the ratio between the rise and the run. So the slope tells us how fast that line goes up for every unit change in the input variable. Okay. What about the b? Well, if you look at that formula, if I put x equals 0, then that means that y becomes exactly b. So the way we interpret b is that b is going to be what we call the intercept, or the value of the function when x is 0, so when the input is 0. Sometimes this has meaning, practical meaning, applied meaning, sometimes it doesn't. Okay.